Welcome to Mass Spectrometry and Isotopes. In an earlier video, we discussed how Dalton said that atoms of different elements can be distinguished by their mass. Since then, we've learned that that's not entirely true, that atoms of different elements are actually distinguished by their number of protons, or atomic number. He also said that atoms of a single element were all identical. In this lesson, we'll look at how that isn't the case, and that there are variations called isotopes. So let's start by talking about how isotopes were discovered. J.J. Thomson, we talked about him before. He had the chocolate chip cookie model of the atom, or the plum pudding model. He also invented a process called mass spectrometry. We call mass spec for short. You saw a simulation of a mass spec in class, but in case you missed it, I'm going to briefly go over how a mass spec works and how it sort of led to the discovery of isotopes. Let's start by defining mass spec. Mass spectrometry is a process that allows us to determine the mass of an object based on its deflection through a magnetic field. So here we have the device, and we'll start labeling this. Now down here we have our source of particles, and in this chamber they're going to get a charge, they're going to get ionized. The second component to the mass spec is that we have a very large magnet sort of wrapped around this tube. So this is a big magnet. So basically this path travels through a magnetic field, and if we have particles that have a charge, they will respond to that magnetic field. So here's what happens. If a particle does not have a charge, it will continue to move straight and collide with that wall. If a particle does have a charge, we're going to see something different happen instead. We're going to see it get deflected by the magnetic field and then go hit our big detector plate that we have on the side here. Now, as we saw in class, the degree to which this particle gets deflected is dependent on its mass. A heavier particle would be deflected less. A lighter particle would be deflected more. So if we have multiple paths coming out of the same source of particles, we can tell what range of masses those particles have. So let's look at an example of this. Here we have another mass spec. We have a magnet wrapped around the pathway, and in this particular mass spec, for our source of particles, we are going to put pure chlorine gas. And in this chamber, the chlorine particles are going to get a charge, they're going to be ionized, and if Dalton is to be believed, and all these chlorines are exactly identical to each other, they should all have the same exact mass, then we should see one pathway of particles being deflected and hitting our detector screen. Now what we see in this case is that we have one path of particle gets deflected and hits the screen here, and then we have a second path that follows very closely and gets deflected just a little bit less. And so from a pure sample of chlorine, we're seeing two paths of particles. What this tells us is that there has to be two different particles of chlorine that have different masses from each other. We can also tell which one of these collisions happens more frequently, because as the detector screen, it will detect which location is being hit more often. So this tells us that we actually have two types of chlorine. We have a chlorine particle that has a mass of 37, and we have a chlorine particle that has a mass of 35. We also know that this one, the 35 mass, is far more common. Atoms of the same element can be different from each other. We've established that they have different masses, and we have a name for that. Atoms of the same element that have different masses are called isotopes. So let's look at some examples of isotopes. Let's look at carbon. Particularly, we're going to look at the nucleus of carbon atoms. So here's one nucleus of a carbon atom, and it has 6 protons and 6 neutrons. So this particular carbon atom that has this nucleus has a mass number of 12. We can represent that as 12C. Note I'm not writing the proton or atomic number because it's implied. If I know what the element symbol is, it's sort of implied what the atomic number is because I can just look that up. Let's look at another nucleus. In this nucleus, we're going to have 6 protons, and let's say we have 8 neutrons. Okay? Now the mass number is 14. So I have an isotope of carbon. Okay, these are both isotopes of carbon. They're the same element, but they have different masses. And that mass came from, we can see that mass came from additional neutrons. Now what happens if I have this nucleus? Is this an isotope of carbon? Well, it has a mass of 14, 7 plus 7 is 14, but wait, it has 7 protons. So this is not carbon, because carbon always has to have 6 protons. This is actually nitrogen, which is not an isotope of carbon because it's a different element. So this is not an isotope. Okay, that's not an example of an isotope of carbon. Now 12C, 14C, this is one way of representing isotopes. We can also write out carbon-12, carbon-12, so the name of the element followed by the mass number, and then this one would correspondingly be carbon-14. So either one of these two notations is perfectly okay, and you'll probably see both at different times. It's just a way of representing the mass number and specifying which isotope of the element you're dealing with. So in this video we've talked about how a mass spec works and how it relates mass and charge together, and you can use it to figure out the masses of particles in a substance. We also talked about what isotopes are and how we can represent them. Any questions you have from this, make sure you write them down in your notes and bring them with you to class.